Hi students, we are back at the end of chapter 5 and Jim Bob has joined us. So Jim Bob gets a job at a chair factory and his boss tells him, I'm going to lunch and when I come back you better have made 5 chairs or you're fired. And Jim Bob happily gets to work, and when he does, he sees that he has 32 arms, 18 legs, 4 backs, and 2 seats. And he stands there with a confused look and says, I guess I'm going to get fired. And the reason is why? Well, the easiest thing to see is he's only got 2 seats there. And if you're going to make a chair, you're going to have something for somebody to sit on. And Jim Bob's boss wants him to make 5 chairs, but he's only got 2 seats. So probably Jim Bob is just going to make 2 chairs, and the boss is going to come back and get mad, and then he's going to explain, and all will be okay. Unless Jim Bob's boss really wants to get rid of him, then he can. But what we've come into contact with here is something called the limiting factor. Now, what is going to limit the number of chairs that Jim Bob can make? Well, it's the seats right there. We only have enough seats to make 2 chairs. We can also look at the backs there. We've only got 4 backs and we want to make 5 chairs. Probably chairs that look like this because that's what's in the picture and not chairs with no backs on them. But you guys get the idea that if you have a part of the whole that you only have a little bit of, that's going to limit how many whole things you can make, whether it's chairs or molecules or whatever else. So that brings us to this slide that says that we have a limiting factor sometimes when we're doing reactions, and that's also called a limiting reactant or a limiting reagent. We use them all interchangeably. And that is going to dictate how much product we can make. So one of your reactants is going to be limiting, and the other one is going to be in excess. Now, in the chemical industry, we generally take the cheaper one and purposely make that provide that in excess so that all of the more expensive reactant will react and make product. So, excuse me, it's just nap time. Okay, so that brings us to some more math problems. And I know you guys love to do problems with me. So these problems are going to look a whole lot like our problems that we just did on the last lecture series, but what we have to do in these problems is we have to do them twice because we have to figure out which one of our reactants is the limiting factor, and that's going to dictate how much product we can make. So number 1 says you have 10 moles of hydrogen gas and 1 mole of oxygen gas, and we want to know how much water we can make. So the first thing that we have to do is figure out the equation for this reaction because we don't have it here. It's not given to us. So we have hydrogen gas, and that's reacting with oxygen gas, and that's giving us water. And that would be in the gas form until we cooled it down, and then it would be in the liquid form. Okay, so if we go to balance these, we'll see that our hydrogens are balanced. So we move on to oxygen. And over here we have 2 oxygens, and over here we have 1 oxygen. And you can't take the O2 and break it apart, so you're going to have 2 waters because each water brings 1 oxygen. And that means you messed up the balance on the hydrogens, but that's okay, you can go back and fix it. So we'll put a 2 there, and then you can put a 1 in front of the O2 if you need it there. All right, so we had to do that little bit of work before we started with any numerical givens. Now it says that you have 10 moles of hydrogen and you have 1 mole of oxygen. How much water can you make? Well, we have to figure out how much water we can make with the 10 moles of hydrogen and how much water we can make with the 1 mole of O2, and figure out who is the limiting reactant. Is it hydrogen or is it water? And how much product can we make in grams? Now, if you look at 10 versus 1, you might think, oh, it's really super obvious who's the limiting reactant. It's probably going to be O2. But I'm going to warn you that it doesn't always work like that. It's not always the one that has the lower number that's going to be limiting. And we will see that in one of the following problems. Okay, so we've got 10 moles of hydrogen, and we want to get to water, and we're already in moles, so we don't need to get out of grams and go to moles. We're already in moles, so we're going to put moles of hydrogen down there, and we want to go to water, so we're going to put moles of water on the top, because whenever we need to go from one substance to another substance, we need the what? The mole to mole ratio. Now, where do I find the numbers that go next to mole in the numerator and the denominator? I find those right off of the balanced equation. So for every 2 moles of hydrogen gas you consume, you're going to produce 2 moles of water. Now, like we did in the other lectures, if mole bothers you, just cover it up with your finger and say to yourself, okay, for every 2 H2s that I use, I'm going to produce 2 waters. And yes, you can reduce the 2 over 2 to 1 over 1, but you know what? Most of us will just leave it like that for simplicity. So we've canceled out our moles of hydrogen, and now we're in moles of water. And we want to get out of moles of water because generally when we see something that says how much, it means that somebody needs to be able to measure it. And most of us don't have a scale that does moles of substances. Most of us have scales or balances that do milligrams or grams. And sometimes we can measure gases in volume or liquids in volume and use densities. So here we're going to put 1 mole of water on the bottom, and we're going to put grams of water on the top because that's where we want to go. And we decided in one of the other lectures that a water's going to weigh 18.02 because we have 16 from the oxygen and we have 1.01 from each hydrogen. Again, if you guys got 18.01 because you used 15.9999 and something else for hydrogen that had a different sig fig on the end, is that okay? Yes, because the last sig fig is where we have wiggle room, so that's okay. So we're going to cancel out the moles of water here. And what we're going to find is that we have 180 grams of water. But we want it to have 3 sig figs. So what do we have to do to 180? We have to put a dot on the end there to indicate that that 0 is significant. Okay, so with that 10 moles of hydrogen, you could possibly make 180 grams of water. Now, let's see how much water we can make with our 1 mole of oxygen. So we have 1 mole of O2, and we're going to go through the same process. We're already in moles, so we don't need the molar mass. What we need is the mole to mole ratio, because we're going from one substance to another substance. And if we look right at the balanced equation, we can see that for every 1 mole of O2, we are going to make 2 moles of water. Okay? Again, if moles bugs you, cover it up and say, I need to consume 1 O2 in order to spit out 2 H2Os. And that means that we have canceled out our moles of O2. And like we did in the above equation, we need to get to grams of H2O. So we're going to do 1 mole of H2O has a mass of 18.02 grams. And that's going to give us 36.0 grams of water. Now, looking at these two masses, you have enough hydrogen to make 180 grams of water, but you only have enough oxygen to make 36 grams of water. So you can't make 180 grams of water because you don't have enough oxygen to do that. You only have enough oxygen to make 36 grams of water. That means that oxygen is your limiting reactant. You could also write that up here. So that's your limiting reactant right there. That means that what is in excess? Your hydrogen. You have excess hydrogen. So this right here is your excess reactant. Or you could have labeled it up here, excess reactant. So your limiting reactant is going to dictate how much of your product you can make. Now on a quiz or a test, make sure that you label the limiting reactant and the excess reactant as reactants. So make sure they're over here. Some students, they like to point to this right here and call that the limiting reactant. Water is not a reactant. Water is your product. So don't make that mistake. And also remember that limiting reactant is also called limiting reagent or limiting factor. Same thing. Okay, we're gonna burn 10.2 moles of propane with 7.8 moles of oxygen, and we want to know how much carbon dioxide we're going to produce. So the first thing we need to do with this equation is what? Is figure out what the equation is. So propane is C3H8, and it says it's a combustion reaction. So we've learned that you have a hydrocarbon and you have oxygen, and that burns and it gives you 2 products, carbon dioxide and water. And we've learned how to balance these, and the hydrocarbons with an odd number of carbons are the easier ones to balance. So we've got 3 carbons from our propane, so that means we're going to need 3 carbon dioxides. And then we have 8 hydrogens in our propane, so that means we're going to have 4 waters because each water brings with it 2 hydrogens, so it's 4 times 2 is 8. And then over on the product side, your 3 carbon dioxides, those are going to provide 6 oxygens. And then your waters, your 4 waters, are going to provide an additional 4 oxygens. So 6 and 4 is 10. Now, over on the reactant side, the oxygens come in pairs. So how many pairs of oxygens do I need to make 10 oxygens? That would be 5, because 5 times 2 is 10. Okay, so you can write your 1 in front of the propane if you need it. Again, if you don't need it, don't put anything there and we'll assume it's 1. All right, so we've got 10 moles of propane and we've got 7.8 moles of O2. And we need to figure out how much carbon dioxide we can produce. So we're going to go through the process we did in number 1 with the math, trying to figure out which one's our limiting reactant, which one's an excess, and how much product we can possibly make. So we go ahead and we write 10.2 moles of propane. And we're going to get out of moles of propane. And we're going to go where? We're going to go to moles of CO2. Because we've got the mole to mole ratio there. Now, if we consume 1 mole of propane, we're going to produce how many moles of CO2? 3. I got that right off of the balanced equation. So moles of propane cancel out, and now I'm in moles of CO2. And now I can go to grams of CO2. So 1 mole of CO2 is going to be a certain mass of CO2. And we figured this out beforehand in one of the other lectures, and we said that that is 44.00. So moles of CO2 cancel out there, and we get 10.2 times 3 times 44.00, and that's going to give us 1346.4 grams of carbon dioxide. And we need 3 sig figs. So here's 1, 2, 3, and then we have to look at the 6 to let us know whether we're going to round up that 4 or not, and we do. So we have 1, 3, 5. Now, 135 is not the same as 1300-ish. So what we have to do is replace that 6 with a 0, and that's going to be 1350 instead of 135. So we've got a placeholder right there, but we don't have a decimal after that 0 because we do not want the 0 to be significant. So 1346 rounds up to 1350, and we're going to put grams of CO2 on the end there. Okay, so right now we can possibly make 1350 grams of CO2, but we have to see if we have enough oxygen to make that much. So we go ahead and we do this all over again because we all love to do calculations. Yippee! Okay, so 7.80 moles of O2. We're already in moles, so we can do a mole to mole ratio. So moles of O2, where do we want to go? We want to go to moles of CO2, just like we did above. Now, if we consume 5 moles of O2, and I got that from right there, we can spit out 3 moles of CO2. Okay, again, you guys, if mole bothers you, put your finger over it and say, I've got to use up 5 moles of O2 in order to make 3 moles of CO2. Or the other way you can say it is, to make 3 moles of CO2, I've got to consume 5 moles of O2. Or 3 CO2s, I've got to consume 5 O2s. Okay, so we cancel out the moles of O2 and we're in CO2, and we write exactly what we did before up here, that 1 mole of CO2 is 44.00 grams of CO2. And if you've forgotten how we do that, carbon weighs on average 12.01 and an oxygen weighs 15.999. So we have 16 plus 16 plus 12, and that's giving us 44-ish. Okay? All right, so we cancel out the moles of CO2. We do the math, and that gives us 205.92 grams of CO2. And again, we want 3 significant digits here. So we've got 1, 2, 3 here, and we take a look at 9 to tell us whether we're going to round that 5 up or not. And we do. So we end up with 206 grams of CO2. So we can either make 1,350 grams of CO2 or 206 grams of CO2. But what's the answer? How much can we officially make? What's 100% yield? That's going to be 206. We don't have enough reactants to make 1,350 grams. We have enough propane to do that, but we don't have enough oxygen to do that. We only have enough oxygen to make 206 grams of CO2. So that means that oxygen, that's going to be your what? That's your limiting reactant. And that means that propane is what? That's in excess, or that's your excess reactant. Okay, again, do not point at CO2 and write limiting reactant, because CO2 is a product. So it's definitely not a limiting reactant because it's a reactant or it's a product, either way. Okay, it's not both. All right, so that is number 2. And that brings us to another problem. Yay! Okay, so this one says you've got 2.3 moles of carbon disulfide, and it's going to react with 5.4 moles of oxygen to form carbon dioxide and sulfur dioxide. What mass of sulfur dioxide is formed? Okay, so we've got to put together the what first? The balanced equation. So carbon disulfide, you guys know how to do this. What we see is we've got the prefix di there, so yay, it's telling us how much of each. So we have a carbon disulfide is reacting with oxygen. Now, when we say it reacts with oxygen, oxygen naturally occurs as O2. So I know that's a little bit confusing, but whenever you read a problem and it looks like that, is going to be the O2 version. Okay, so reacts with oxygen to form carbon dioxide, and we know what the formula for carbon dioxide is. And sulfur dioxide. So we have SO2. Okay, so when we go to balance the equation, we can see that our first element, carbon, we've got one of those on both sides, so we're good there. And then carbon disulfide. We've got 2 sulfurs there, so that means we're going to need to go over to the product side and have 2 sulfurs there too. And who brings the sulfur? Well, that's sulfur dioxide. So we're going to need 2 of those. And that means that on the product side, we now have 4 oxygens coming from the 2 SO2s. And we have 2 oxygens coming from that 1 CO2 that we have there. So we have 4 plus 2, which is 6. And over on the reactant side, the oxygens come in pairs. So how many O2s do I need to make 6 individual oxygens? That would be 3. 3 times 2 is 6. So if you guys need to write the ones in, write the ones in. If not, that's cool too. So you have 1, 3, 1, 2 there. Okay, now that we've got the balanced equation out of the way, we can start doing the math. And that's really where you want it to be, right? Because we're all here for the word problems, because everybody loves word problems, right? Ha, 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 ha. Okay, so what's given to us is 2.3 moles of carbon disulfide. And we want to know how much sulfur dioxide is formed. Okay, we're already in moles, so we don't have to go grams to moles. And when we're already in moles, we can go right to the mole to mole ratio, which is where we switch from one substance to another substance. And where do we find the numbers that go right next to the MOL and the MOL in the conversion factor there? Right off the equation. So if we consume 1 CS2, we're going to make how many SO2s? 2 of them. Okay? So if you make 2 moles of SO2, you must have consumed 1 mole of CS2. Okay, so moles of CS2 cancel out, and we're in moles of SO2. So we're going to need a molar mass to go ahead and go to grams of SO2. So when we have the molar mass, we always want to write 1 next to mole, which is obviously different in the mole to mole ratio, so don't confuse those two. So we've got 1 mole of SO2, and we want to know what the mass of that is. So we would go to our periodic table, and we would go ahead and add this up. So you've got 16 plus 16 for your oxygens, and that's 32. And then you'd have another 32 for your sulfur, and you would get about 64.1. And if you don't trust me, take a look at the periodic table and you'll see. A sulfur weighs about 32, and each of your oxygens weigh about 16. And that's going to add up to about 64.1. And again, we made this 3 sig figs because our original value had 2 sig figs. And convention states that we usually want to go 1 more sig fig than whatever our lowest number of sig fig measurement is there. Okay, so we cancel out moles of SO2, and if you guys do the math on this, what you're going to get is 294.86 grams of SO2. Now we already said that over here we've got 2 sig figs. The 2, the 1, and the 1, those are exact, so we can ignore those because they have an infinite number of sig figs. And then we purposely made this one 3 sig figs, so it won't constrict the number of sig figs. So 1 and 2, and then we look at the 4 to tell us whether we're going to round up that 9 or not, and we do not. So we have 2, 9, and then we need to put that 0 in there as a placeholder because 29 is completely different from 290. So we're going to put 290 grams of SO2 there. And so we can possibly make 290 grams of SO2, but we need to see how much SO2 we can form with that 5.4 moles of oxygen. So right now, if we just look at the problem, we'll see we've got 2.3 moles of carbon disulfide and 5.4 moles of oxygen. So it probably looks to you like the 2.3 moles of carbon disulfide, that's going to be your limiting reactant because 2.3 is less than 5.4. But let's see if it works out that way because it doesn't always work out the way we think it's going to work out. Okay, so we've got 5.4 moles of O2 We're already in moles, so we can go right to our mole to mole ratio. So we've got moles of O2. And on top, we have moles of SO2 because that's the substance we want to go to. And we need to consume 3 moles of O2 in order to get 2 moles of SO2. So our moles of O2 cancel out. And then we said if you've got 1 mole of SO2, that's going to be a mass of about 64.1 grams of SO2. So our moles of SO2 cancel out. And if we calculate that out, what we'll see is that we get 230.76 grams of SO2. And we've got 2 sig figs here that we started with. And again, we're going to ignore 2, 3, and 1 because they're exact numbers. And we purposely made this one 3. So 2 sig figs. So we've got 2 and 3. And we're going to look at 0 to tell us whether we're going to round 3 up to 4 or not. And obviously we don't. So what we have here is 230 grams of SO2. So with this amount of O2, you can only make 230 grams of SO2, and that's a lot less than 290. So we have enough carbon disulfide to make 290 grams of SO2, but we only have enough O2 to make 230 grams of SO2, so we cannot make that much SO2. We can only make 230 grams of SO2. So that would be your answer right there. And then if the question asks you to identify your limiting reactant in your excess, it would be O2 that is limiting. And notice that's the bigger number. So 5.4 is bigger than 2.3. So it's not always obvious which one is the limiting reactant. And because O2 is limiting, that means CS2 is your excess reactant. Okay, so we've tackled another problem. So those are pretty big. So number 4 says that we have 5.50 grams of silicon dioxide, and we're going to react that with 4.71 grams of carbon, and we're going to form silicon carbide and carbon monoxide. So what do we need to do first? Write the balanced equation. All right, so silicon dioxide, what we're going to have there is SiO2. I hope that wasn't a bad one for you guys. And that's going to react with carbon. Not carbon with something else, just carbon. And that's okay. Carbon can be reacting on its own. And then we're going to get a couple of products. We're going to get silicon carbide. And that one might sound a little bit strange because we're not used to carbon being carbide, but that's what silicon carbide looks like. And we're going to get also carbon monoxide, which you guys should be familiar with. Okay, so balancing this one, we've got 1 silicon on each side. We've got 2 oxygens from the SiO2. So that means we're going to need 2 carbon monoxides because each one of them brings with it 1 oxygen. And if we look at carbons, we can see that on the product side, we've got 3 carbons, 2 from the 2 carbon monoxides and 1 from the silicon carbide. So we're going to need to put a 3 over here. So you guys can put the 1s there if you would like. Or again, you don't have to put them there. And then we have to do the math. Yay! Just what we were waiting for. Okay, so one of our givens is 5.5 grams of silicon dioxide. So we're going to write that right here. 5.5 grams of silicon dioxide. Now, so far in problems 1, 2, and 3, we've been spoiled because they've started us off with moles. But now we're starting off with grams. And whenever we have grams, we're going to want to go where? To moles. So now we're going to have to do an extra step that we didn't have to do in 1, 2, and 3, which is the molar mass, because we have to get rid of grams and go to moles, and when we're relating grams and moles, that is the molar mass. So we're going to have grams of silicon dioxide on the bottom here because we want to get rid of grams of silicon dioxide up there. And we're going to have moles of silicon dioxide up here because we need to get to moles so we can get to a mole to mole ratio so we can switch over to carbon monoxide. All right, whenever we're in a molar mass, you're going to have 1 next to the mole, and then for the mass of silicon dioxide, you guys are going to need to add that up. And what we'll see is that you have 60.08 for that. And if you need to check my math, go ahead and pull out your periodic table and add up the silicon and 2 oxygens and wait a minute here. Oh, okay. I was looking up here and I was like, why is this one 64.1? And that's because it's sulfur dioxide, not silicon dioxide. Okay, scared myself there. Okay, all right. So we're going to go ahead and cancel off the grams of silicon dioxide. And now we're in moles of silicon dioxide, so we can go to mole to mole ratio. So moles of silicon dioxide down here. And where do we want to go? We want to go to moles of carbon monoxide, CO. And for every 1 silicon dioxide that we consume, we are going to create 2 carbon monoxides. So moles of silicon dioxide cancels out. And then we want to get to mass. So we're going to need to use a molar mass. So that relates moles to grams and grams to moles. So we have 1 mole of carbon monoxide. And if we add a carbon and an oxygen together, what we're going to get is 28.01-ish, depending on which sig figs you use, which periodic table you use. So when we do all of this math, what we're going to get is 5.128 grams of carbon monoxide. And that right there, oops, I shouldn't have tried to put a box around that yet. So we have 5.128, but we want 3 sig figs. So we've got 1, 2, 3 there, and we look at the 8 to tell us whether we're going to round the 2 up or not. And indeed we do. So we have 5.13 grams of carbon monoxide that we can possibly make from the amount of silicon dioxide that we have. But we have to figure out how much carbon monoxide we can make with the amount of carbon that we have. So we'll go ahead and do the math for that one. So we have 4.71 grams of carbon, and we need to get the molar mass for carbon. Oops, that's grams of carbon down there. Let me move it over a little bit so I have some more room. Grams of carbon. And 1 mole of carbon up there. Okay, so how many grams of carbon per every mole of carbon? Where do you find that? Well, you find it right off the periodic table. The periodic table will tell you that if you've got a mole of carbon, on average, you've got 12.01 grams. Okay, so grams of carbon cancel out. And we want the mole to mole ratio because we need to get from carbon to carbon dioxide. So for every 3 moles of carbon that we consume, we're going to make 2 moles of carbon monoxide. That other carbon goes to the silicon carbide. So that's why it's a ratio of 2 to 3 and not 3 to 3. Okay, so the moles cancel out. And now that we're in moles of carbon monoxide, we need to go to grams of carbon monoxide. And that's a molar mass. So the number 1 goes next to moles. So we have 1 mole of carbon monoxide, and then we have grams of carbon monoxide on the top. And up here we calculated it to be 28.01. And we cancel out the moles of carbon monoxide. And what we get is we get 7.323 grams of carbon monoxide. And we have 3 sig figs here, so it's 1, 2, 3, and we take a look at that 3, which will tell us whether we round the 2 up or not, and we don't. So we have 7.32 grams of carbon monoxide that we can possibly make from this amount of carbon. Now, how much can we make? How much carbon monoxide? We can make 5.13 grams because we don't have enough silicon dioxide to make 7.32 grams of carbon monoxide. We only have enough silicon dioxide to make 5.13. So we can't make 7.32. So this means that our silicon dioxide is our what? That is our limiting reactant. And that means that carbon is your what? That's your excess reactant, or reagent, or factor. Again, you guys, don't point to carbon monoxide and call that the limiting or excess reactant, because that's not a reactant, it's a product. All right, so in the next video, we'll do percent yield and we'll do a couple of problems, and then we'll be on to chapter 6. Yay! Okay, you guys, bye-bye.